But anyways, before we do that, let's check the answers. So what one do I need to continue from? We did this one. Did we do the answers for electric field potentials? I don't think so.
What's the way is the course of work deadline?
Don't worry, we'll start this week.
Oh, okay.
Now.
No.
Okay, question 1. What answer did you get, Ben?
4 times minus 17.
Correct. Question 2.
No.
No? Oh, you didn't do this?
I will do this.
Ah, Ben! You need to do this.
Okay.
Right on the top.
Okay.
To do this.
Do
this. Okay, right. Well, what about the next page? Did you do that one?
I think we had.
Oh yeah, we checked that one. Yeah. Okay, the next page.
Maybe checked.
Yeah, but I don't know if we checked it. What did you get for the first one, Ben?
9.6.
Correct. Next.
9.02.
Correct. Next.
2160.
Correct. Next.
18.8.
Correct. Next.
6.45.
6.
17.7.
17.7. Yeah.
Okay.
Yeah. Yeah. Next.
3.7 10 minus 3.
Good. Next.
3.7
Good.
10 minus 2.
Next.
0.377.
Good. The last one.
Oh, you say this is.
Oh yeah, no, important.
Fun.
Important. Right, next. First one. Oh, right on the top to do this.
Do this.
Okay. You have 2 to do.
Okay.
Okay. Next. Right, first one.
440.
Next.
Really?
Good, yeah.
Okay.
Next, number 2.
I have to find this. Oh, it's 2.6.
Good. Number 3.
0.26.
Good. Number 4.
No.
Not yet. Okay, fine. No, it's okay. And next one. We did this. Yeah, we started this one last time. What would you get for the first one, Summer?
I forget the answer. I just
2.28 times minus 7.
Good. Next.
It's 2.25 times 6.
Good. Next.
Next, I don't know. My answer is correct or.
What did you get for number 3?
Is this one? I think it's wrong, so I didn't continue because the speed is too big. The speed square is the speed is 1.5 to 10 29 times.
Well, what about the next one, number 4? No? Number 5?
No.
Oh, you're not finished this. Finish this. So now you have 2.5 to do.
Yes.
Okay. Well, when you finish it, we'll check the answers then next time, okay? Let's continue with the next lesson, Newton's law.
Newton's. Oh, it's
Yeah?
3. Oh, no, it's 3rd.
Oh, he has more.
Oh.
He's very busy.
Maybe we will have a test before the next holiday.
Maybe. We'll see. Okay. Dropbox. DIFC. workbook, physics, fields, Newton, open. Load in.
Free space.
A lot of free space.
Yeah.
A lot. Because I only use this in class.
Oh.
Right, write that down. Newton's law. Now, Newton is very important. He did a lot of work. So he has another law. So as you know, the Earth pulls other masses to it, and the Sun pulls the planets, such as the Earth, towards it. So there must be some kind of field, like an electric field or a magnetic field around the Earth. So I'll draw a picture. You remember, if this is negative and this is positive, it will move in, because there's a field around it. Now, this is Earth, and this is you, or whatever. It will also move down. So by the same idea, there must be some kind of field around the Earth as well. So we imagine that there is a field around the Earth. We call it a gravitational field. It would look something like this. Now the black, that's the field lines. And do you remember what these red circles are called? Do you remember what those are called? No? Forgot the name?
Not the gravity.
Say again?
Gravity.
No. Equipotential. Do you remember this word? No?
Increased potential.
Equipotential. Oh dear. Okay.
Potential and
Yeah. Exactly. Look, I'll draw it for you. Okay, these are the gravitational. Oh my goodness, my spelling. Gravitational field lines. And then in red, the potential energy is the same.
See?
On this line, everywhere on this line, the potential energy is the same.
Yeah.
Everywhere on this line, it's the same. So we call these red ones equipotential lines. You remember this name?
I know the equal.
There, yeah. Equi means equal. I'm unhappy you forgot this name. So can you draw this?
Just you say with this write down, I know.
Okay.
Just pronounce I don't know. What is this?
Well, you should know how I pronounce it.
Actually, I think the right one is O3.
O3? O3? Oh. O3. Ozone, yeah. No, not that. Yeah?
Uh, yeah.
Yeah? Continue? Okay. So, it was discovered by Newton that masses attract other masses. The bigger the mass, the more force. Closer it is, more force. So we were talking about this a little bit the last time. Yeah? This is Newton's formula for the force between two masses. Now usually one of these is very big and the other one's very small. Usually, okay? And the G, well, F is the force, M is the masses, R is the distance between the centres, and G is a constant, which is very small actually. That's the value of G. Okay? Have you seen this before?
Yeah.
Yeah? You've seen this before? Okay. You got that? Right, so. Notice how similar this is to Coulomb's law. What we've not said yet is what the field strength is. The field strength E in an electric field was force per unit charge. Okay, so remember the E, the field strength, that was force per charge, right? What do you think the field strength is for gravity? Well, it's going to be the same, except it's not force per charge. What do you think it might be? Force per...
Potential and
Nope. Nice try. Nope. Any ideas, Ben? What causes the force in an electric field? What I mean is, like you have a proton and an electron. Why is there a force? Huh?
Ionization.
Yeah. Because it has a charge.
Yeah.
Okay. So why do you have a gravitational field? Because you have a...
Mass.
Correct. So what do you think the field strength is? Yeah.
For mass.
That's it. So for gravitational field strength, we use the letter G, is the amount of force per mass in the field. So as a formula, it's just F over m. So if I was to imagine here, we have an m and we have an F, then we say the field strength is F over m. That's the gravitational field strength.
So write the box. Just write
You could just write gravitational field strength G equals F over m. Yeah? Yeah. Okay, so we have a formula for F. So let's put a small mass near a large mass. Let's see what formula we get, okay? So look, if we look at this picture, actually since I have it here, that's GMM over R squared over m, small m. So the small m's cancel, and you're left with GM over R squared. Okay, that's another formula. Oh, and of course the units, newtons per kilogram.
So we have a very long unit.
Oh, what do you mean?
This unit just have two. One is a Newton, the other is a kilogram.
Oh,
per
can you
kilogram.
change it? Yes, we'll see that later. Continue. Continue.
Second. Okay.
Right. Let's calculate how strong the gravitational field is at the surface of the Earth. So here you are, we're in a gravitational field, okay? And I want to know how strong this field is. So what if you can use this formula, okay? This is the mass of the Earth. This is the radius of the Earth in kilometers. Change it to meters. Okay, so tell me, oh, you have the G? 6.67? Yeah? Right, tell me what this field strength is. Looks familiar? Don't tell Ben, let him be surprised. Oh no. Square. Yeah. Where have we seen that number before? Yeah. So this G, which is newtons per kilogram, is the same as this G. They're the same. It's interesting, right? Why are they the same? Well, if you think about it, G equals F over M, F equals MA, so G equals A.
Yeah.
Makes sense? Okay. So just, you don't have to write this down, just a review. All masses produce a gravitational field which attract other masses. The force can be found using this formula. Fields always point towards the centre of the mass. The field around a small mass can be ignored when compared to a bigger mass. Because masses are positive, the fields never point out but only in. The strength of the field can be found using that formula, and this is in fact the same as acceleration. That's what we've learned so far. And the value of G near the surface of the Earth is about 9.81. Okay? Right. Now remember, when one mass is trapped by another mass, then it will have negative potential energy. Remember that? From Coulomb. Yeah. And here's the formula. Now, does this look familiar? It looks the same as the one we did last time.
Yeah.
Except instead of K, it's G.
K, Q.
Yeah, and instead of Q's, it's M's. Okay. So this is the formula for potential energy when you have like, let's say, Earth, Moon. And the Moon has a negative potential energy because it's trapped. Okay. So you need this formula. Where's Go? Got that?
Why the more wouldn't go around of the sun.
Because
Too far away.
yeah, it's closer to the Earth. So if you were to free the moon, maybe you'll go around the sun. Maybe. Okay, but don't we have this formula? Oh, yeah. Let's see what's happening, because we have two formulas. It looks like. So let me explain what's happening. Okay. Right. So we'll call this R, and this H, and here and here. There's two potential energies. Which one is bigger? The one on the top is bigger, and the one on the bottom is smaller. Isn't that right? Because yeah, if you look at the formula here, a big R means this is nearly zero, which means it's bigger because of the minus. So if I move this from here up to here, I give it energy. How much energy do I give it? So I give it energy. How much do I give it? I will give it minus gm over R plus H, minus gm over R. Okay, well look, you see that there's a gm in both, and this is 1 over R minus 1 over R plus H. Okay, so far? So, this is gmm 1 over R minus 1 over R 1 plus H over R. Is that okay? I took the R out. Now, call or let x equal minus H over R. So this is equal to gmm over R, because you have R here and here now.
Yeah.
1 minus 1 over 1 minus x.
Yeah.
Which equals gmm over R 1 minus 1 plus x squared, da, da, da. You remember this from maths?
Yeah.
You remember this? It's the same as this. We did. You did that in maths. Okay? So that's equal to gmm over R 1 minus 1 minus x squared, da, 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 da. But this is very small, isn't it? H over R. You know, this could be like 10 meters, and this could be 6,000 meters. So if x is very small, then x squared is so small, we don't care about it. Too small. Okay? Right. Well, let's continue. Minus x is that. So this is gmm H over R squared. That's equal to m. That's equal to m gm over R squared H. What's gm over R squared?
G.
Same. So if you move between two energy levels near the surface of the Earth, you can use this formula, or you can use this formula. It's the same answer. It's nice. Yeah? I like it.
Yeah.
I like it. You don't need this for the exam. This is only for interest. Yeah? Just for interest.
We can't use MGH.
No, you can. I'm saying the proof.
Oh.
Not necessary for the exam. Okay. Right, Newton's law of gravity gives the size of force between two masses. This force is one of the four basic forces. We talked about this last time. We have electrostatic, gravity, and two more,
Yeah.
which I'll tell you later. Secret for now. It's an example of an inverse square law. Remember we talked about that inverse square law? No?
Square law?
Forgot this?
Which class?
The last class.
Last class.
The last class. No?
It's three constant.
Thing?
Three constant thing over.
Yeah, that's it. Yeah, that's it. Yeah. Right. Here's a short, easy question. Now maybe this is too easy. What is the force between the Earth and the Moon? Okay, so we just put in the numbers and let's calculate it. There's the mass of the Earth, the Moon, and there's the distance.
Yeah.
So tell me what the force is.
.59, 10, 28.
Okay. Did you get that, Ben?
Oh, I think I lost the square.
What'd you get, Ben?
Hmm? What?
Hmm?
It's 1,000. It's 38500 times 1,000.
It's minus.
I think your answer is right because the ANS is
Can I see yours, Ben? What you
I
did?
think that's is right.
Ah, yeah. But Ben's very smart, you know.
Yeah.
Oh no, Ben's is wrong.
What? What?
Ben forgot the 10 to the power minus 11.
No, I minus. It's 46 minus 11. So it's 35.
Oh, I understand. I understand. You didn't forget it. Good job. You're right. It's 24, 22, 1.97 times 10 to the 20?
What? Why my answer is 1.95?
I don't know.
Oh.
Ah, it doesn't matter.
Plus 97.
Yeah. We'll continue. Right, now, wait, you need to keep that answer. Do you still have that answer?
Yeah, I have.
Right, let's write it down. What was it, Ben? F equals, yeah?
1.97.
Yes.
Test
20 newtons. Okay, now my next question for you is how long does it take the moon to orbit the Earth? Time now.
It's F.
F equals m omega squared, or, yeah. So F over m or root equals omega,
Yeah.
which is equal to 2 pi over t. So t is 2 pi root root m r over f, isn't it? Yeah.
It's
So we know the or, we know the f. What's the m here? Which one? Earth or moon? Which is it?
What?
The m here,
Yeah.
is it the Earth's mass or the moon's mass?
the moon's mass.
Correct, moon. Okay, right. Give me the time, so.
Okay.
Oh.
Should be a big number.
No, 1.97.
No.
No,
Big number, right? Show me.
no, it's a small number.
What? Show me. Oh, your root.
My root have something wrong?
Yeah, root's not big enough.
This.
Correct. Now wait, Ben has it.
Oh.
Now, Ben, change that seconds, change that into hours. Divide by 3,600.
3,000.
600. Right, show me. Okay, now change it into days. Divide by 24. Right? The moon takes 28 days to go around, doesn't it?
Oh, maybe.
I think it does.
Yeah.
So, you know, this is good.
Okay.
Yeah? Okay.
It's same.
Yeah.
Yeah.
Okay, good. Last one is how much potential energy does a satellite have? You know satellite?
I don't know.
Satellite. You don't know this word. Okay, Earth.
Oh. Okay.
Satellite. How much potential energy does a satellite have that is 35,786 kilometers above the surface of the Earth? Now wait. Above the surface of the Earth.
8.
So I've given you this distance. And you can't use MGH because the H is too big. It only works when it's small. Okay?
But also we can use R.
Well, you know
we
this.
have to.
Yes, yeah.
Fast
Yes.
pace.
Uh-huh. Oh. Somewhere.
Yeah.
Maybe.
I think I didn't lose
Let me calculate.
something.
What's the 100?
100
And-
solid. 100,000. And
22? What is 22? So
And the other one is
No, this is the answer. What did you get? No.
what? Where?
I'll write it down before I give you the calculator. Its energy is minus 94456,199.4, which is equal to minus 945 megajoules. That's the answer.
oh, I squared it.
Yeah, don't square.
Oh yeah, it's the same.
Yeah.
This, yes.
Yeah. So what that means, yeah, it's quite different. If you have a satellite here and you want to free it,
Oh, you have more.
yeah, you have to give it 945 megajoules to free it. Yeah. It's a lot, isn't it?
Yes.
It's a lot. What?
What thing I lost? I think I didn't lose anything.
Got the wrong answer?
Yeah.
You have to give it energy. Yeah. Yeah. Now, what do you think? If it was here, with this 945 part, would it be bigger or smaller?
Oh.
The 945. Would it be a bigger number or a smaller number if it was here instead?
Small.
Well, like, what do you mean? Do you mean 945? It might be like 935?
I think it's bigger because the R is small.
Yeah, it's bigger because the R is smaller. So maybe for example, oh, actually, if you have the calculator, we could calculate it. So if we just put the distance at 0,
Oh.
you know what I mean?
Yeah.
Let's see what it is. What's the radius of the Earth? 6371.
Oh.
Oh, much different. 6250 megajoules. So that's 6.25 gigajoules. That's why rockets are so big. They need lots of energy to be very big. Okay. Good. I'm happy. I'll let you try these for a few minutes. Not too difficult, right? Right?
Just use GM.
It's G.